Tonight, we're going to explore one of the biggest changes SpaceX has made to its vision for humanity beyond Earth. For years, almost everything pointed toward Mars. Starship was being built to carry people and enormous amounts of cargo across interplanetary space, with the eventual goal of creating a permanent civilization there. But now, the first city SpaceX wants to build beyond Earth may be on the Moon. Elon Musk has described a plan for Moonbase Alpha, not simply a research station, but a settlement designed to keep expanding. Starships could deliver habitats, machinery, robots, power systems, and eventually factories. Lunar resources could provide water, oxygen, construction materials, and propellant. Over time, the goal would be to manufacture more locally, rely less on Earth, and turn a collection of landed spacecraft into something approaching a self-growing city. And that may be the real reason the Moon has moved ahead of Mars. Mars has not disappeared from the plan. SpaceX may instead be trying to prove the hardest part of the Mars vision somewhere else first. Whether a settlement beyond Earth can repair itself, expand its infrastructure, use local resources, and gradually become less dependent on supplies from home. If that works on the Moon, Mars becomes the next place to repeat it. By the end of tonight, you're going to understand how SpaceX's proposed lunar settlement could grow from landed starships into habitats, industry, and local infrastructure, why self-sufficiency matters far more than simply reaching another world, and what success on the Moon would truly prove for Mars. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Before asking how SpaceX could possibly build something this large on the Moon, there is a more fundamental question. Why build there at all? Earth is already the place where life works. It gives us liquid water. It gives us breathable air. It gives us an atmosphere thick enough to hold both. It gives us a biosphere, the living web of plants, animals, microbes, soils and seas that has been shaping itself for billions of years. It gives us familiar gravity. It gives us climates where a person can step outside without wearing a pressure vessel. The Moon gives us none of that. There is no air there to breathe, no open water, no weather that carries rain across a field, no forest, soil, or food web waiting beyond the horizon. There is only rock, dust, darkness, sunlight, and vacuum. Vacuum means almost no matter at all. It is a place where an unprotected human body cannot remain alive. So the question comes first, and it should. Why leave the one world that has already done so much of the work for us? Earth is not finished. Climate change remains. Inequality remains. Infrastructure needs repair. Resources are strained. Whole communities need safety, energy, food, water, housing, and opportunity now, not in some distant future. A rocket leaving the ground does not make those obligations disappear. This is where the proposal needs to be understood clearly. It is not an argument that Earth is ruined. It is not an evacuation plan for a discarded home. And it is not a promise that another world will solve the problems we have chosen not to solve here. Earth remains home. The source frames expansion as an option, an additional project, something people and institutions may choose to attempt while the work of caring for Earth continues. That distinction matters. A civilization can try to build elsewhere without pretending that its first world has become expendable. But here is where it gets strange. The comfort of Earth can hide how little of our own neighborhood we occupy. The Sun contains 99.86% of the mass in the solar system. If all that mass were divided into 10,000 grains of rice, 9,186 grains would belong to the Sun. Earth accounts for about 0.003%. That is 3 grains out of a million. Think about a true scale diagram of the solar system. You shrink the Sun until it can fit on a page. Then, you look for the planets. Most of them nearly vanish. Earth becomes a microscopic speck beside the vast weight of the Sun and the empty distances around it. And on that speck, every human story has unfolded. Every city, Every language, every machine, every war, every work of art, every scientific discovery, all of them have occupied a share of the solar system so small that on the right diagram, it is almost invisible. That does not make Earth unimportant. It makes Earth more remarkable. One small world has carried all of this. The familiar challenge asks why we should leave the only comfortable planet. The reversal asks something different. Why should a technological civilization permanently confine every possible future to 3 grains in a million? Not an escape, an expansion. Not because Earth has failed, because the future may hold more than one place where human beings can live, work, learn, and endure. That feeling has an older echo. Roughly 70,000 years ago, human populations began expanding outward from Africa. That is about 700 human lifetimes of 100 years each. No one beginning that movement could have known the later shape of Europe, the Americas, the internet, or spaceflight. Those futures were not visible at the start. They became possible because people moved, adapted, and built in places their ancestors had never seen. The analogy can be useful. It gives the impulse a human scale. Movement opens futures that cannot be predicted in advance. But the analogy breaks at the airlock. Terrestrial migrants remained inside a biosphere. They crossed land and water, but the air was still there. Gravity was still there. Food webs were still there. Weather could be harsh, but it was weather. There were roots back. There were places where the body could breathe. A lunar settler crosses into vacuum. Every breath must be carried or made. Every safe temperature must be maintained. Radiation, high-energy particles arriving from the sun and deeper space must be blocked by walls, soil, or shelter. Crops must be grown inside a controlled system. Water must be cleaned and used again. Spare parts must arrive or be made before a small failure becomes a larger one. The moon is not another continent. It is not a harder journey. It is a different category of journey. The migration story explains motive. It does not solve the engineering. It does not turn a dead landscape into a place that keeps people alive. And it does not answer the question of cost. Large space programs use public money, private capital, skilled labor, factories, launch sites, and years of attention. They carry schedule risk. They carry technical risk. Current lunar plans can produce high-skill industry, communication systems, robotics, energy technology, and scientific knowledge. Those benefits can be real. They can be additive. They do not automatically settle the moral argument. We do not know the exact balance in advance. No equation can prove that off-world investment outranks every need on Earth. That remains a value judgment. The strongest case is not that the moon deserves everything. It is that exploration can add capabilities without asking us to stop caring for the place that made us possible. And the current is broader than one company or one person. Elon Musk and SpaceX describe the largest and fastest version of the ambition in this source. But NASA is building a moon-to-Mars architecture. China has long-term lunar station plans. Commercial delivery programs are developing. Multiple lander providers are competing to reach the surface. This is not a private fantasy. It is a strategic current. Several institutions are asking whether a lasting human presence beyond Earth can be built carefully enough to matter. They are not all offering the same answer. They are not all moving at the same speed, but they are looking toward the same hard boundary, the airlock. The impulse to explore can carry us that far. Beyond it, every comforting idea must become machinery, and that machinery has to work. The machinery has to work somewhere first. That is why the moon returns to the picture. SpaceX has long been associated with Mars, the red world far beyond our nearest orbit. So a place called Moonbase Alpha can sound like a retreat, a smaller destination, a distraction from the original promise. But the destination may not be the deepest point. The deeper point is whether we can build a settlement at all. Can we carry people there? Keep them alive? Repair what breaks? Add new capacity? Learn from each failure before the next one matters more. The moon may be valuable because it gives us more chances to answer those questions. Not Mars abandoned. Mars rehearsed. The Moon sits about 384,400 kilometers from Earth. It is still a vast crossing, but direct journeys usually take 2 to 5 days. Apollo crews made the trip in about 3 days. A broken valve, a revised procedure, or a new crew can reach the site on the scale of a working week, not a season. Mars changes the rhythm completely. The Mars 2020 mission took about 7 months to arrive. Once a crew has left, a forgotten tool is not waiting on the next launch. A repair team is not a few days behind them. The distance turns ordinary maintenance into a long act of planning. Think about a nearby test range. A machine fails. You inspect it, change one part, and test again. The Moon offers more of that pattern. Mars makes each experiment much longer, but here is where the comparison needs care. The Moon is not available at any hour. A landing site has geometry, it has lighting, it has limits imposed by the energy of the journey. Apollo-style missions could have only a few hours in a month for a particular opportunity. Even so, crew opportunities are often described as roughly monthly. Efficient departures to Mars return about every 26 months. Future high-energy stages could broaden some lunar access toward daily or nearly daily windows. The difference is real. The Moon is more available. It is not unconstrained. That correction matters. A monthly opportunity is still a narrow opening, but compared with a 26-month rhythm, it can support many more learning cycles. And then there is the silence between Earth and the crew. For one lunar architecture comparison, total communication latency can be up to about 14 seconds. Latency means the delay between a message leaving one place and arriving at another. 14 seconds is long enough to notice. It is short enough for guidance to feel nearly conversational. Mars is different. A message takes roughly 4 to 24 minutes in one direction. A crew facing an emergency may finish the first diagnosis before Earth even hears the beginning of the problem. The answer from home then has to cross the distance again. Wait. The Moon does not remove danger. It changes who can respond to it. On the Moon, a team can exchange observations with Earth while the event is still unfolding. On Mars, the crew must carry more of the decision inside the habitat. That is not a small operational detail. It is a different texture of isolation. Abort options show the same divide. A lunar abort can bring people home in hours or days. A Mars abort may require months or years, or may not be practical. The crew may have to stabilize the situation with what is already around them. So the Moon can function as a nearby test range. It can also be a down payment on Mars. Not because a lunar failure is harmless, it is not. But because a failure can be visited, understood, and answered across many missions before it becomes a multi-year trap. This is the shorter feedback loop. A feedback loop is the cycle in which an attempt produces evidence, and that evidence changes the next attempt. Shorter travel, more frequent opportunities, faster guidance, more recoverable failures. Each one can turn a proposal into data sooner. And that is why a Moon-first strategy can still point toward Mars. As of August 2026, the broader architecture is written in 4 parts: human lunar return, foundational exploration, sustained lunar evolution, humans to Mars. The order says something quiet but important. The lunar stages are meant to test transportation, communications, habitation, mobility, power, local commodities, autonomy, and logistics before the farther campaign. Local commodities means useful materials made or gathered near the settlement. Autonomy means the ability to keep operating without immediate instruction from Earth. Logistics means the organized flow of cargo, spares, crews, and supplies. None of these is glamorous by itself. Together they decide whether a base remains a visit or becomes a place that can persist. Commercial deliveries add another kind of practice. A payload must be integrated. A lander must descend. Equipment must survive the surface. Multiple lander providers add dissimilar approaches, meaning that one design failure does not automatically stop every path to the Moon. China and Russia have also described an international lunar research station. Its stated work includes long-duration autonomous operation, resource surveys, resource use, experiments, and technology verification. Even its schedule contains a useful warning. One account places a Chinese lunar mission in 2028. Another places it around 2029. The destination is shared. The calendar is still unsettled. This is a wider attempt to learn whether sustained lunar work can make later exploration less blind. The transferable lessons are substantial. Deep space habitation means living in a sealed environment far from ordinary support. Closed-loop life support means recovering water and air instead of discarding them. Modular interfaces, standard connections for power and replacement, can be tested. So can local oxygen or propellant production. Propellant is the material a rocket uses to move. Precision landing, surface power, EVA systems, mobility, autonomous maintenance, cargo aggregation, and the discipline of operating beyond immediate support can all be practiced there. EVA means the suits, tools, and procedures used outside the habitat. But here is where it gets strange. The rehearsal has missing acts. Mars has an atmosphere, thin but real. A human-scale landing there must use atmospheric deceleration, slowing down in air before propulsive descent, the rocket-powered final approach. It must also manage the way engine exhaust strikes the surface. It must guide a large vehicle through conditions the airless moon cannot reproduce. The gap is not cosmetic. It is physical. It is operational. It is unavoidable. The moon cannot validate a months-long Mars transit. It has about 1/6 of Earth gravity, so each step would feel far lighter than it does at home. It cannot duplicate Mars chemistry, surface conditions, or the need to verify a safe system before a crew begins the long journey. The temperatures underline the mismatch. In full sun, a lunar surface example reaches about 260 degrees Fahrenheit, hotter than a home oven. In darkness, it can fall to minus 280 degrees Fahrenheit, colder than a household freezer by a vast margin. The moon also has almost no atmosphere, no global magnetic shield, sharp dust, and micrometeoroid exposure, tiny natural fragments moving through space. Mars asks different questions. Its atmosphere changes descent. Its gravity changes bodies and machines. Its long travel time changes rescue. A system can work on the moon and still fail for Mars-specific reasons. Not a copy. A rehearsal with limits. That is the real strategic boundary. A lunar base may reduce risk for selected capabilities. It may make habitation, power, local resources, autonomy, and logistics more mature. It may expose weaknesses early enough to correct them, but it cannot certify a Mars mission simply by existing. We do not know yet how much lunar infrastructure should be optimized for local work, and how much should be designed to transfer onward. We do not know whether resource demonstrations become reliable industry, and we do not know whether the shorter cycle reduces total calendar time or total cost. The formal strategy supports risk reduction. It does not prove the shortcut. The next question is what those words, settlement, independence, and growth, would have to mean when the supply ships do not arrive. Before the moon can count as proof, settlement has to become more precise. A base can remain occupied for years. That alone does not make it independent. The next supply ship may still carry every meal, every filter, every medicine, every sensor, and every computer the crew needs. Think about a village on the coast of a new continent. At first, ships arrive with tools, food, parts, and people. Then, one day, the expected ships stop coming. The decisive question is simple. Can the village continue? On the moon, the question is harder. The village must make or preserve its own air. It must control its own temperature. It must treat its own water. It must maintain the barrier between its people and radiation. The surrounding environment is not merely difficult, it has to be manufactured. That is why the words matter. Continuously occupied, permanent, regenerative, partially self-sufficient, self-sustaining, self-reliant, self-growing. They can sound like different ways of saying the same thing. They are not. The first rung is a continuously occupied base. It keeps a defined crew alive between planned resupply missions. It holds emergency stores. It can isolate a failure. it can shelter the crew or return them home. Its permanence describes occupancy or infrastructure. It does not describe independence. The second rung is partial self-sufficiency. Here, the settlement repeatedly regenerates selected essentials. It measures what still leaks away, and it lowers the imported mass needed for each resident in each year. Water may be recovered, oxygen may be regenerated, waste may be processed. Some food calories may be grown. Local material may become shielding or construction. Power may become more available, but each stream has to be measured separately. This is not one grade, it is a scorecard. The third rung is self-sustaining. Essential consumables are regenerated or obtained locally for long intervals, but that is only half the test. The settlement also needs repair capability, spare inventories, fault diagnosis, medical support, and redundancy. Redundancy means a second path exists when the first one fails. The fourth rung is self-growing. This is the hard threshold. A city must add habitat, power, life support, transport, and industrial capacity without importing an equal or larger mass of productive equipment. Productive equipment means the machines and tools that make more useful machines and tools. It is not only surviving, it is reproducing the capacity to survive, and that changes the meaning of growth. More rooms are not enough. More people are not enough. A city that grows while its maintenance burden grows even faster has not crossed the threshold. It has expanded its cargo schedule, but something was wrong. A permanently inhabited base can still be a very elaborate delivery address, not independence, reliable resupply, not a self-growing city, a staffed outpost. Not until the vital streams close and the equipment that closes them can itself be maintained. Current life support systems show both the promise and the gap. A regenerative system reuses air and water and aims to produce food. A closed ecological system tries to connect waste processing, bioreactors, filtration, and photosynthesis. Bioreactors are living systems that use organisms to change one material into another. Photosynthesis is the process by which plants use light to make food. The International Space Station remains semi-closed. It recovers some important streams. It still depends on filters, spares, maintenance, and regular logistics from Earth. That is not a failure. It is an honest description of where the technology stands. The water number makes this clear. A 98% water recovery demonstration is a major achievement, rising from roughly 93 to 94%. Imagine collecting 100 cups of water. 98 cups return to use. 2 cups are gone. That is excellent recovery. It is not total closure. Those 2 missing cups must still come from somewhere. And water is only one stream. Oxygen has its own losses. Food has its own limits. Nutrients, medicines, filters, electronics, and factory parts have theirs. Wait. Closing one loop does not close the settlement. A closure scorecard is more useful than a single grade. It asks how much water is recovered and how much makeup water is needed. Makeup water is the new supply required to replace what the system loses. It asks how much oxygen returns to the system and how much atmosphere escapes. It asks what fraction of calories and nutrients are produced locally. It also asks what happens to waste. Can nutrients be recovered? How much of the construction and radiation shielding comes from local material? Is there a continuous power margin, meaning extra power beyond ordinary demand? How many consumables and spares arrive from Earth for each person each year? How long can the settlement endure a missed resupply? Then come the questions that are easier to overlook. Which critical faults can be repaired locally? Can the city expand while imports per resident fall? Or does every added room require an even larger stream of replacement hardware from Earth? The pump inside the water recycler reveals the problem. The settlement may recover nearly all of its water, but a pump bearing wears out. A bearing is the small component that lets a rotating part move smoothly. If no one can replace it, the recycler becomes a silent box. The water loop was not enough, not because the recycling failed, because the maintenance loop remained open. The machine needed a bearing. The bearing needed a supply chain. And the supply chain still reached back to Earth. Supportability has its own closure curve. Supportability means the ability to inspect, diagnose, repair, and return equipment to service. Smaller replaceable units can reduce spare mass, but they can also multiply the variety of parts, the diagnostic complexity, and the skill needed to repair them. This is where the hidden imports gather. Catalysts, seals, bearings, lubricants, complex electronics, sensors, medical goods, precision tools. A catalyst is a material that helps a chemical reaction proceed. A seal prevents a gas or liquid from escaping. These may remain imported long after the settlement can make walls, oxygen, and shielding. Biological closure is wider still. Calories alone do not describe it. A mature settlement has to track water, oxygen, nitrogen, carbon, waste, nutrients, energy, and health. At a genuinely permanent stage, it must eventually consider genetic diversity, the range of inherited variation needed across generations. We do not know the minimum population needed for that final kind of resilience. No established number in this plan can certify it. Medical, industrial, biological, and social endurance remain linked problems. So what would the Moon have to demonstrate before it became a graduation test for Mars? First, it would need to operate the scorecard across multiple cycles. Second, it would need deliberately introduce faults, failures placed into the system so the crew can show how they respond. Third, it would need to endure a realistic gap in resupply. Then it would need useful infrastructure made and qualified locally. Qualified means tested well enough for a real operational role. The crew would need to demonstrate autonomy, the ability to keep working without immediate direction from Earth. An added capacity would have to avoid creating a faster growing maintenance burden. The Moon can test those processes. It cannot reproduce a months-long Mars transit. It cannot reproduce Mars communication isolation. It cannot turn a lunar abort into a Martian one, not the destination itself. A demanding rehearsal. The source speaks of a self-growing lunar city in under 10 years, less time than a child spends in school, and Mars in 20 plus years, close to a generation. Those are aspirations, not universal certification thresholds. We do not have one agreed number that says the settlement has become self-sustaining. We do not have one measured line that proves it can reproduce its whole industrial, medical, and repair base. The dates can move. What matters is the rung reached and the streams that have truly closed. Next comes the heavier question of what all that capability would have to carry. Once self-growth is defined, the million-ton number stops being a spectacle. It becomes a box that has to be unpacked. The source proposes roughly 1 million metric tons for a Moonbase Alpha scale settlement. That is a useful scale claim. It is not an authoritative requirement for every lunar city. The real total would change with population, the degree of closure, the chosen site, the shielding strategy, the maturity of local resources, the industrial scope, and the reserves carried against failure. So let us put the number on a shoreline first. An ultra-large container vessel is one of the biggest cargo ships on Earth. It can carry around 150,000 tons, including its containers. 1 million tons is more than 6.5 of those vessels. Picture 6 great ships at a port, then another half ship behind them. That is the mass in the claim. But water does most of the work for those ships. They cross an ocean, they meet a port, cranes lower containers onto a road or rail network already waiting for them. Lunar cargo has a different journey. It must survive launch. It must reach orbit. It must be refueled. It must travel onward. It must land. It must be unloaded. Then it has to be joined into a working surface system. The number is not a delivery count. It is an industrial chain. Historical studies make that chain easier to see. One lunar base model described a settlement of 18 to 20 people after 10 years, enough people to fill a modest dining room. It had 5 habitation modules, 5 research units, 3 production plants, 2 workshops, 3 power units, an earth mover or crane, 3 mobility units. That arrangement matters because it is not only a collection of rooms. It has places to live. It has places to study. It has machinery that makes and moves useful things. It has power. It has mobility. It has the beginnings of maintenance. The common modules in that study were 4.5 meters wide, about the width of 2 parked cars, and 11 meters long, about the length of a city bus. Each held up to 17.5 metric tons of contents. This was an outpost with production, not a self-growing city. Another partial gravity habitat study routed 570 metric tons through low Earth orbit. Low Earth orbit is the band of space close above our planet where spacecraft circle Earth. That mass is more than 30 of the smaller 17.5-ton modules. Its lunar modules were roughly 35 tons each, about the mass of 2 of those earlier modules. Even there, pressurized living space was only one line in the manifest. Transportation and shielding were lines beside it. Now comes the crucial calculation. Divide 1 million tons by 17.5 tons. You get roughly 57,000 common modules. The headline changes shape, not thousands of rooms, tens of thousands of modules, not a campsite, an industrial network, not one finished settlement, a vast inventory whose purpose has to be named. Pressure-rated habitats and airlocks would be part of it. An airlock is the sealed chamber that lets people and cargo pass between a pressurized room and the vacuum outside. So would power generation and distribution, the equipment that makes electricity and carries it where it is needed. Life support processors would be there. Food and starter nutrients, rovers, cranes, excavators, and maintenance vehicles, communications and navigation systems, laboratories and medical systems. Then the list becomes quieter and more important. Resource processing plants, factory tools, metrology, which means precise measurement equipment, computers, sensors, catalysts that help chemical reactions proceed, seals that keep gas and liquid from escaping, bearings that let rotating parts move smoothly, lubricants, specialty chemicals, spare modules, emergency stores, construction hardware. This is why no defensible percentage can be assigned to habitats, machinery, food, or reserves from the available evidence. Each category depends on the others. A workshop without power is stored mass. A refinery without replacement parts is temporary. A habitat without air processing is only a shell. The picture did not hold. The moon can eventually replace some of the heaviest things in that box. Regolith is the broken rock and dust covering the lunar surface. In one summary, more than 40% of it is oxygen by mass. In every 100 kilograms of that material, more than 40 kilograms are oxygen bound inside minerals. More than 90% is silicate minerals, the family of materials that includes the ingredients of glass and many kinds of rock. The moon is not empty material. It contains iron, aluminum, titanium, silicon-bearing minerals, glassy material. Aggregate, the crushed mineral material used in construction. That can become oxygen, slag, glass, ceramics, simple metals, berms, which are raised walls of soil, landing pads, roads, foundations, radiation shielding, large structures that do not need perfect precision. This is a profound change in the cargo mix. Local material could displace immense bulk mass. A city would no longer need to lift every wall, every road, and every layer of shielding from Earth. But the moon is a quarry. Not a complete warehouse. Water remains conditional. We have confirmed water signatures and trapped volatile materials in polar regions. Volatiles are substances that can evaporate or be released as gas. But a signature is not a mine plan. It does not tell us the concentration at a chosen site. It does not tell us the depth, form, accessibility, or cost of recovery. A credible settlement manifest still needs prospecting, drilling, heating, vapor collection, purification, storage, and reserves for a poor deposit. Carbon and nitrogen may be the quieter limit. Ordinary lunar regolith is not known as a complete biological or electronics warehouse. Polar compounds may contain carbon and nitrogen-bearing material. That does not establish reserves large enough for a settlement. Food systems, polymers, specialty chemistry, and biological inventory would still begin with imported stocks and careful recovery. The same limit appears inside an oxygen plant. A historical model aimed to produce at least 30 tons of oxygen each month. That is 360 tons in a year, about the mass of 20 common modules. It is a substantial utility. It could support a base and its vehicles. It does not make food. It does not make electronics. It does not make medicine. And it does not make itself. Local oxygen closes one utility. It does not close the city. The scale of excavation gives the same warning. A current demonstrator aims to move on the order of 20 tons of regolith in one mission. A little more than one historical module of contents. 1 million imported tons is 50,000 times the handled amount, and that count excludes the far larger local mass that may be moved for shielding, pads, roads, and foundations. The work is not only hauling cargo from Earth, it is becoming able to handle material where it lies. Reserves cannot be reduced to one reassuring percentage. Some spacecraft concepts use examples such as 30% dry mass growth or 30% power margin. That means 3 extra units for every 10 in a planning allowance. Those are design examples. They are not settlement defaults. The useful question is failure consequence. Which parts can be replaced? Which systems have a second path? How much food and water can wait quietly in storage? What construction losses are expected? What emergency stock remains after a missed delivery? Each answer changes the mass of the box. At first, the cargo mix is complete systems and consumables. Then come processing plants, farms, spares, test equipment, and redundancy. Redundancy means a second path exists when the first one fails. Later, if the settlement truly advances, Earth cargo becomes smaller and more complex. Precision tools, electronics, sensors, medicines, specialized chemicals. Meanwhile, the local mass begins to do the heavy work. Structure, oxygen, glass, wire, shielding, power surfaces. That is the test of the million-ton idea. Not whether the number sounds large enough. Whether each delivery gradually changes from a finished imported system into the compact machinery that helps the settlement make more of its own world. Before any category can become local, its first machines still have to cross the distance. That makes transport the next part of the ledger. Solar panels cannot wait quietly for batteries. Habitats cannot do much without power. Factories need vehicles, spares, food, tools, and the systems that keep people alive. A lunar settlement is an ordered construction sequence. If the power hardware arrives late, a habitat already on the surface can become an expensive sealed room with no useful work around it. This is why the source needs a vehicle unlike the rockets we have used before. It needs large payloads, it needs reuse, it needs a lower price ambition, and it needs repeated production on a scale closer to freight than to occasional exploration. Falcon 9 gives the source a useful contrast. Its historical average was about one launch every 2.2 days, a little longer than a weekend. That is already an extraordinary rhythm for orbital flight, but a million-ton settlement would need a much larger vehicle, moving far more mass, far more often. Starship is the proposed answer. As of June 2026, SpaceX described version 3, or V3, as targeting 100 metric tons to low Earth orbit in a fully reusable configuration. Low Earth orbit is the band of space close above Earth, where spacecraft circle the planet. 100 metric tons is about the mass of 6 of the earlier lunar cargo modules together. It is a design target. It is not a flown payload delivery. A later generation could potentially reach 200 metric tons to orbit, perhaps V4. That would be twice the V3 target. It would still be an orbital figure, not a lunar surface delivery. That distinction changes the whole picture. Not a moon truck, an orbital target, not demonstrated cargo, a proposed capacity, not one destination, several different architectures. One refilled moon architecture describes up to 100 tons reaching the lunar surface. One human landing system design presentation also showed about 1,200 metric tons of propellant, roughly 69 of the earlier cargo modules, serving a payload above 100 tons. A separate contracted cargo service describes roughly 12 to 15 tons to the surface for particular missions no earlier than fiscal year 2032, a load closer to a heavily packed delivery van than to a 100-ton shipment. These are not competing measurements of one vehicle. They are different configurations, different commitments, and different points in an unfinished system. The vehicle itself is still immense. The V3 stack is listed at 124.4 meters tall, about the height of a 40-story building. It is 9 meters wide, roughly the width of 3 cars parked side by side. At liftoff, it is about 5,433,000 kilograms, or 5,533 metric tons, more than 300 of those earlier cargo modules gathered in one machine. It has 39 Raptor engines, nearly enough to fill a small classroom with one engine at every desk. 33 sit on Super Heavy, the booster below. 6 sit on the ship above, about the number of people around a large dining table. A Raptor is a rocket engine designed to burn methane and oxygen. Super Heavy is the first stage, the immense lower vehicle that lifts Starship away from Earth. Those dimensions explain the wonder. They do not establish the freight service. The source pictured early 2026 V3 flights, Flight 12 in March, and only 10 to 20 V3 flights before V4. But by June 2026, SpaceX reported 12 total Starship flight tests, and expected V3 payload delivery in the second half of 2026. The short V3 run is therefore a source projection, not a verified production plan. The same caution belongs to the larger V4 image. The source describes a 142-meter vehicle, about a 45-story building, with 42 engines, more engines than chairs around a large conference table. Those details were not verified here. The possible 200-ton payload to orbit has primary support. The height and engine count remain claims from the source. But the test program has achieved meaningful things. Starship has completed successful ascent events. Super Heavy has returned and been caught. A booster has been reused. Upper stages have made controlled re-entries. One return came within 3 meters of its intended point, close enough to place a vehicle beside a small backyard gate. Engines have relit in space. These are real steps. They matter. They are not the whole campaign. But here is the harder boundary. About 5 metric tons of cryogenic propellant have been moved between tanks inside one Starship. Cryogenic propellant is fuel kept extremely cold, so it remains liquid. 5 tons is about the mass of 2 family cars. That is not orbital refueling. It is not 2 vehicles together. It is not hundreds of tons. Lunar logistics would require one Starship to launch, another to launch, both to rendezvous, both to dock, their liquids to settle, their lines to chill, their inventories to be measured, and their load to remain usable after they separate. In low gravity, the fuel does not simply rest at the bottom of a tank. It has to be managed. As of August 2026, vehicle-to-vehicle transfer remained a critical planned demonstration. This is the difference between a component test and a transport network. The first shows that a valve, a tank, and a flow path can work inside one vehicle. The second must show that an entire chain can work repeatedly between vehicles, across many launches, with a lunar mission waiting at the far end. Cadence is where the million-ton dream becomes most demanding. A 200-ton vehicle flown rarely cannot build a million-ton city. Commercial aviation is the image behind the proposal. Vehicles return. They are inspected. They are prepared. They fly again. Yet aircraft-like operation is an aspiration. There is no public evidence that fixes a qualified V3 or V4 fleet size, vehicle lifetime, turnaround time, unit production rate, or sustained daily flight rate. Reuse is a valuable capability. It is not proof of frequent reuse. The reliability arithmetic is quiet, but it matters just as much. Consider an illustrative chain of 12 independent required events. At 99% success for each event, the chance that every event succeeds is about 88.6%. In 100 such complete campaigns, more than 11 would fail somewhere in the chain. Raise each event to 99.9%, and the chain reaches about 98.8%, leaving a little more than one incomplete campaign in 100. Not poor individual performance. Compounding risk. Not one launch. A linked campaign. Not routine yet. A threshold still to earn. Historical lunar concepts have used 16 launches, including 14 tankers, a support spacecraft, and a lander. More recent discussions often mention at least 12 V3 missions, while still treating the final count as ambiguous. The exact number depends on the architecture. The lesson does not. Each required event adds another link. For people, the standard rises again. Human rating does not come from one dramatic recovery. It comes from repeated safe return, fault tolerance, abort or escape logic where it applies, and reliability over the lifetime of the system. Fault tolerance means a dangerous failure has another path around it. A fleet intended to carry crews has to demonstrate that protection again and again. Cost remains even less settled. The original HLS development contract was worth $4.3 billion, more than $1 billion for each of 4 years of work. By December 2025, its potential value was roughly 6% higher, or $253 million more. HLS means Human Landing System, the lunar lander architecture developed for NASA. But a development contract is not the price of hauling freight. The operating model would still include vehicles and engines, manufacturing, pads, propellant production and loading, tankers and depots, recovery, inspection, refurbishment, static tests, licensing, environmental mitigation, losses. The price of a mature cargo fleet cannot be calculated from public information yet. Neither can its final tanker count, its vehicle life, its turnaround, or its sustained output. Starship may become the enabling machine for this kind of settlement. But before it becomes a lunar freight system, every promising test has to become a repeated link in the chain. The next number makes that chain look almost simple, until the hidden assumptions begin to appear. That apparent simplicity begins with division. Suppose for a moment that the 200-ton vehicle exists exactly as imagined. The million-ton city can then be divided into days. 1 million tons is too large to hold in the mind for long. It is 6 great container ships and another half ship. It is an industrial landscape compressed into a single number. But a daily flight count feels different. A flight count feels like a timetable. You can picture a vehicle rising in the morning, another returning to a pad, another being prepared somewhere beyond the horizon. This is the source's most persuasive move. It takes a civilizational cargo mass and keeps dividing until it looks like an operations schedule. And the first comparison is meant to make that schedule feel even more manageable. The source places New Glenn beside Starship. New Glenn is Blue Origin's large rocket. It associates an announced 9x4 upgrade with 70 tons to low Earth orbit, or LEO, the region of space close to Earth. That is about 4 of the earlier lunar cargo modules placed into orbit. It also uses a 200-ton comparison, then says 3 launches could reach that total, perhaps over roughly 1 week at a future Falcon 9-like cadence. The comparison cannot carry the conclusion placed on it. As of August 2026, public New Glenn figures are 45 metric tons to low Earth orbit, about the mass of 3 loaded city buses, and more than 13 metric tons to geostationary transfer orbit, or GTO, an elongated path toward a much higher orbit. 13 tons is a little less than 1 loaded city bus. No established public figure gives New Glenn a direct lunar surface payload. The 200-ton and 70-ton claims are not reconciled with those figures, so they cannot establish a fair cost comparison. They cannot establish lunar throughput either. That does not make Starship simple by comparison. A rocket brochure tells us what a vehicle might lift toward low Earth orbit. It does not tell us what reaches the lunar ground. Blue Moon, Blue Origin's lunar lander system, uses more than a single launch. It includes a transporter or depot, a storage and transfer station in orbit. It includes refuelers, vehicles that bring propellant. It includes transfers in low Earth orbit, movement to a higher stair-step orbit, and another transfer near the Moon. Starship also needs a depot and multiple tanker flights before a lunar vehicle departs. The useful comparison is not one rocket against another. It is one complete chain against another. Now, the arithmetic can begin. The source grants Starship 200 tons to orbit. One such launch each day produces 1,400 tons after 7 days, about 80 of the earlier 17.5-ton lunar modules. Under the source's 5 refueling flight assumption, that weekly orbital mass becomes one 200-ton delivery to the Moon. The same idea can be pushed much further. One 200-ton launch each hour gives 4,800 tons per day. That is enough mass to equal more than 270 of those earlier cargo modules in a single day. Multiply by 365 days. The result is 1,252,000 tons per year, usually rounded to 1.7 million tons. Nearly 2 million tons. Almost twice the proposed city mass in 1 year. The source compares those 4,800 daily tons with roughly a year of present SpaceX orbital mass. That comparison should remain a moving scale image, not a fixed benchmark. Annual launch mass changes quickly, but the image does its work. An hourly cadence would be a discontinuity in throughput, a different order of activity. And then the calculation makes its first clean turn. The city is not supposed to arrive in 1 year. It is spread across 10 years. 1 million tons divided by 10 becomes 100,000 tons delivered to the lunar surface each year, enough to fill about 5,700 of the historical modules used as a reference earlier in this story. Divide again. At 200 tons per cargo Starship, the annual requirement becomes 500 lunar cargo deliveries. 500 arrivals in 1 year. A little more than 1 cargo landing each day, on average. Then add the source's fixed refueling assumption. 5 tanker launches for every cargo ship. 500 cargo flights require 2,500 tanker flights. Add the cargo flights themselves. The total is 3,000 launches per year. Divide 3,000 by 365. The answer is about 8.22 launches per day. Conventionally, 8.2. Not 24 launches each day. 8.2. Not an hourly departure. A conditional average. That is the first reveal, and it is a fair one. If every source assumption holds together, the million-ton city does not require the full hourly cadence. The clean average appears to leave margin below it. The arithmetic is not hard. It is almost soothing. But here is the hidden calculation. 8.2 is the visible answer in a spreadsheet with hidden cells. The cells contain the parts that determine whether the answer describes a real campaign. First, the source treats 200 tons as lunar-delivered cargo. The supported future figure is instead an orbital target. Public descriptions of a refilled lunar mission give up to 100 tons to the surface. Some specific lunar cargo service concepts are lower still. Change 200 lunar tons into 100 lunar tons, and the cargo count doubles before a single tanker has been added. The result changes quickly. 500 cargo landings become 1,000. Not a small correction. A doubled transport burden, a doubled landing burden, a doubled unloading burden. Second, the 5 tanker flights are simply entered as a fixed value. They are not derived in the source calculation. Historical concepts use 14 tankers. Current descriptions refer to more than 10 for a crewed lander campaign, with the final number depending on actual performance. A mature cargo architecture might eventually use 5. We do not know yet, but the calculation does not show how that number was earned. Third, the visible count omits the support around the cargo flights. Depot launches, extra propellant flights, reserves for transfer losses. A depot is not a passive tank. It is a working storage point in orbit, exposed to the slow loss of very cold propellant called boil-off. Every cargo ship must be full. Every landing must work. Every load must remain usable after arrival. Then comes ordinary time, weather, pad work, inspection, recovery, fleet downtime, a mishap hold, licensing, propellant production, and loading. None of these are dramatic. All of them take time. The daily average has to survive them. 5 pads were under construction as of June 2026. That establishes an intention to increase activity. It does not establish 3,000 launches each year. It does not establish synchronized recovery. It does not establish propellant supply, regulatory approval, or an 8.2 launch average through weather and maintenance. And there is one final cell. The calculation imports the entire 1 million tons. The city may eventually use lunar material for shielding, roads, structures, oxygen, and other bulk needs. The fraction that must arrive from Earth remains undefined. A smaller imported share lowers the flight count. A larger need for imported machinery, spares, and consumables raises it. So 8.2 launches per day remains useful. It shows that hourly cadence is not a mathematical requirement for 1 million tons over a decade. But it is not an established operational requirement either. It is a scenario result, balanced on payload, tankers, losses, support flights, and downtime. The next question is whether that quiet chain can keep moving from the pad all the way to the moon. The arithmetic ends at the pad. The cargo journey does not. A rocket can clear the tower exactly on schedule and still contribute nothing to a lunar settlement. Its propellant has to begin at a terrestrial production plant. It has to move into tank farms, the large storage fields beside a launch site. It has to reach the pad, fill a tanker, leave Earth, meet other vehicles in orbit, transfer into storage, and remain usable. Then it has to fuel the vehicle going outward. That vehicle has to depart, land, unload, and have its cargo integrated into a working surface system. One missed station can hold the whole line. This is the useful way to picture the present lunar concept as of August 2026. A depot is first launched to low Earth orbit, the ring of space close to our planet where spacecraft circle quickly. A depot is an orbital storage station. Then more than 10 tanker flights arrive. A tanker is a vehicle carrying propellant rather than people or surface cargo. Each must rendezvous, meaning meet at the same point in space, dock, and transfer fuel. The lander is filled from that depot. It leaves for lunar orbit, completes a checkout, meets the crew architecture, descends to the surface, and later carries out its assigned ascent or disposal role. The propellant aggregation begins more than 200 days before a crew launch, longer than half a year. The target rhythm is around one tanker every 6 days, nearly a week between arrivals. Imagine an orbital fuel terminal being assembled and stocked one flight at a time. Each tanker is only one delivery to that terminal. The terminal must stay healthy while the next delivery approaches. A road trip needs gas stations, a lunar mission needs its fuel network. The first operational boundary lies inside that campaign. About 5 metric tons of cryogenic propellant have moved between tanks within one Starship. That is a real result. But an internal transfer is liquid moving inside one vehicle. It does not require 2 spacecraft to find one another, dock gently, manage their shared inventory, and send liquid from a tanker into a receiver. Not the whole operation, one part of it. The rendezvous is still separate. The docking is still separate. The transfer is still separate. As of August 2026, the Sided 2 Starship demonstration for that complete operation remained pending. That is the test that must combine rendezvous, docking, receiver transfer, and inventory control. Inventory control sounds ordinary. In orbit, it is not. The system has to know how much usable propellant remains in each tank, where it is sitting, and whether it will be in the right condition when an engine needs to restart. Cryogenic means kept extremely cold. Methane and oxygen are stored as liquids only because they are chilled to very low temperatures. Methalox is the name for methane and oxygen used together as rocket propellant. Hydrolox uses hydrogen and oxygen instead. Both kinds of propellant need careful management, though their exact temperatures and handling differ. Warmth is the quiet enemy. A cold liquid absorbs heat. It begins to boil. The gas raises pressure inside the tank. Venting can protect the tank, but the vented gas is propellant no longer available for the mission. This loss is called boil-off. It is closer to ice in a warm, pressurized container than fuel in a sealed car tank. Then come the less visible tasks. Transfer lines and receiving tanks need chill down, the process of cooling their surfaces before cold liquid can enter without flashing into gas. The liquid must settle in low gravity, where there is no ordinary bottom of the tank. It must be measured. It must move quickly enough. It must finally reach the engines in restart condition. None of this is impossible. All of it is part of the machine. There is a useful smaller precedent. 42 litres of liquid methane were stored for 4 months with zero boil-off, about the volume of 2 large water cooler bottles kept through an entire season. Cryocoolers, machines that remove heat, and multi-layer insulation, many thin insulating sheets, made that result possible. It validates techniques. It does not validate a Starship depot. The scale is many orders larger. The depot would require active heat removal, mixing, transfer equipment, and operations. Not a passive thermos, a working terminal. The answer was stranger than expected. The depot may be the first place the clean daily average meets ordinary Earth. At Starbase, the analysed environmental case as of August 2026 covers up to 25 launches, 25 ship landings, and 25 booster landings in a year. 25 launch opportunities is about 2 each month. At Kennedy Space Center, LC-39A has analysed up to 44 launches and landings annually, a little under 1 each week. LC-39A is a launch complex. Its analysis does not guarantee a license. Those are not statements of achieved cadence. They are environmental and licensing envelopes, the operating bounds studied for impacts and permission. The source scenario calls for 3,000 launches a year, the same 8.2 daily average already traced through the spreadsheet. That is 120 times a 25 launch annual case. It is roughly 68 times a 44 launch case. 5 hypothetical identical pads could divide that traffic. Real pads are not identical. Each site needs maintenance crews, fueling equipment, range coordination, recovery zones, water, roads, airspace access, shipping, a trained workforce, and room for contingencies. A launch range is the protected land, sea, and air area used during flight. A recovery zone is the area kept ready for a returning vehicle. The local systems have physical scale too. The 25 launch Starbase case estimates 58,450 metric tons of carbon dioxide equivalent from launches each year, more than 10 fully fueled V3 stacks in mass. It estimates another 35,051 metric tons from methane venting, more than 6 such stacks. Carbon dioxide equivalent is a common measure that expresses different warming gases as one comparable climate quantity. The deluge system, which floods the pad with water to absorb sound and heat, required an industrial wastewater permit dated February 18, 2025. At several launches each day, these are not decorative details. Propellant delivery or local production matters. Water handling matters. Noise, roads, airspace, shipping, and nearby communities matter. Environmental review is not outside the architecture. It is one of the stations in the line. And then there is the station no schedule can wish away. An anomaly. Mishap holds are intentional safety behavior. After a serious failure, regulators and operators investigate the event, isolate the fault, and complete corrective actions before return to flight. The Federal Aviation Administration, or FAA, is one of the agencies involved in United States launch oversight. It can delay a vehicle, pad, or fleet. Not wasted time, protected time, not an embarrassment. A necessary pause, not one problem, a possible system problem. A serious lunar freight plan therefore needs spare pads, spare vehicles, fault isolation, and schedule margin. Fault isolation means finding which part failed without grounding every healthy part. Margin means time and capacity held back for the things that will not go exactly as planned. Without both, one anomaly can stop every tanker while a depot is waiting in orbit. Weather creates another queue. A booster catch occupies tower systems. A returning ship needs a window, inspection, and preparation. Tankers from several sites must arrive while the depot storage remains healthy. The slowest station can be vehicle production, or tank farms, or range access, or docking ports, or cryocoolers, or lunar unloading equipment. This is a production line. The slowest station sets the output. Blue Moon has the same broad truth. Its architecture also uses orbital fuel management with a transporter or depot, refuelers, transfers in low Earth orbit, movement to a higher stair-step orbit, and a final cislunar transfer. Cislunar means the space between Earth and the Moon. The distinction is the shape of the logistics and the propellant choice. It is not one system refueling, while the other somehow avoids the problem. So the honest measure is not launches per day. It is reliable tons successfully unloaded and integrated on the Moon each year, after losses, holds, maintenance, weather, transfer limits, landing, and surface work. We do not know that number yet. A reusable tanker propellant, turnaround, boil-off, fleet reliability, and annual delivered cargo are not publicly fixed. And when the cargo finally reaches the surface, the next question becomes even more demanding. Can a landed vehicle become a place where people can safely live? Once the cargo is unloaded, the empty ship remains. It is still the largest object on the site. Returning every landed vehicle could mean discarding the largest delivered piece of construction material. A retained upper stage brings steel structure, pressure-tight volume, tanks, plumbing, electrical pathways, airlocks, and equipment that never had to pass through a separate cargo hatch. The vehicle is not only the truck, it can become part of the town. The source puts the dry upper stage at around 120 tons, mostly steel, about the mass of 20 loaded city buses. It claims that around 90% of this dry mass could become usable surface material. It also proposes up to 200 tons of conversion parts, roughly the mass of 33 loaded city buses, inside a vehicle. The exact version for comparison and the 90% figure are source claims. They have not been independently derived. Still, the idea is elegant. A ship that arrives carrying a building can arrive as one, not an empty shell, a delivered pressure vessel, a ready-made beginning. There are two broad ways to keep it. The first is upright retention. A Starship HLS, the lunar landing version of Starship, stands about 50 meters tall. That is roughly a 15-story building. It would remain on a prepared compacted pad, with purpose-designed anchors, buttresses, utility trunks, elevators, redundant airlocks, and shielding berms around it. A berm is an engineered bank of soil or rock. This preserves the orientation used for landing. But daily life becomes vertical. Every repair, meal, medical response, and evacuation crosses decks. Much of the tall hull also remains hard to cover with protective material. 2 planned airlocks and an elevator may support normal operations. They do not automatically provide an escape route from every deck. The other option is horizontal conversion. First, the ship would be defueled and made safe. Then, the shell would be inspected, lowered under controlled support, anchored, connected to pressurized tunnels, and covered with regolith. Regolith is the broken rock and dust that covers the lunar surface. Laying the hull down could create floor plates that feel more like rooms in a building. It could make burial easier too. But no Starship-class lunar lowering operation has been demonstrated. The Moon has not yet shown us a crane, cradle, anchor system, and robotic work crew that can safely lay down a 50-meter vehicle. It is a new operation, a large one, a mission of its own. Think of converting a used aircraft fuselage into a building. The fuselage gives you a strong outer form, doors, wiring paths, and a pressure shell. But this shell has a harder job. It must continue holding pressure against vacuum for years. It must survive thermal cycling, the repeated expansion and contraction caused by heating and cooling. It must remain trustworthy after the violence of launch and landing. Landing loads matter. Weld history matters. Tank condition matters. So do every hatch, pipe, cable passage, and repair. Non-destructive evaluation means examining a structure for cracks or weakness without cutting it open. Leak testing looks for escaping gas. Proof testing checks whether a component can hold an intended load. Fracture control is the plan for stopping a small crack from becoming a dangerous tear. Not quick inspection. a certification program, not a fresh factory vessel, a flown and landed vessel, not merely a room, a pressure boundary for human lives. Some propellant tanks might become useful volume, others might need cleaning, isolation, or complete exclusion from occupied space. Then the human rating changes too. A flight vehicle is designed for a mission. A residence needs air distributed through all its spaces, humidity control, sanitation, lighting, acoustics, medical space, accessible maintenance, and contamination control. It needs to work on an ordinary day. It needs to work after years of ordinary days. Fire design and escape design are separate problems. A factory can add hot processors, chemicals, batteries, and dust to the risks already inside a pressure shell. Detection finds a problem early. Suppression limits the fire. Smoke control protects breathable paths. Electrical isolation separates failed circuits. Masks and alternate exits give people another route when a primary route is blocked. A tall hull needs those choices built in before people depend on it. But here is the harder boundary. Vacuum does not cool a habitat by blowing heat away. There is no air to carry heat from the steel skin. Heat must travel through designed paths. At equatorial noon, lunar temperatures can reach about 302 degrees Fahrenheit, hotter than the heat inside an oven used for bread. At night, they can fall to minus 292 degrees Fahrenheit, cold enough to immobilize ordinary outdoor machinery. Some eclipse cases can last up to 100 hours, more than 4 days without direct sunlight. The hull needs insulation, pumps, fluid loops, radiators, heaters, and redundant heat rejection. A fluid loop is a circulating liquid system that carries unwanted heat away. A radiator is the surface that releases that heat into space. The steel skin does not solve this. The pumps do not solve it alone. The radiators do not solve it alone. The whole thermal system has to keep working. Dust makes that system harder. Lunar grains are jagged and can cling through electrostatic charge, a force created when surfaces carry tiny imbalances of electricity. They abrade seals and joints. They create leak paths. They contaminate radiators and change the way a surface absorbs and releases heat. One Apollo-era instrument ran about 68 degrees Fahrenheit, hotter than expected, after dust affected its thermal control surface. That is the difference between a comfortably warm room and the air beside a running oven. Every tunnel adds a seal. Every utility line adds a seal. Every docking connection adds a seal. In one dust control experiment, a component seal was tested through 10,000 cycles, like opening and closing a front door every day for more than 27 years. The lunar version must still be inspectable and repairable. Then comes shielding. Useful radiation protection is not a dusting over the ship. Credible concepts use roughly 2, 2.5, or 3 meters of regolith. 3 meters is about the height of a ground floor ceiling. One study of a 2.5 meter berm used a 25-degree slope, a 40-degree internal friction angle, and a safety factor of 1.8. Internal friction describes how well grains resist sliding past each other. A safety factor means building stronger than the minimum expected load. This is earthwork. A tall ship needs a wide, stable berm, not loose dust. Engineered ground. Anchoring is just as local. Regolith can be at least 4 meters deep in many regions. Deeper than a single-story room is tall. A plan cannot assume shallow bedrock. Survey must come first. Then compaction, broad footings, soil anchors, berm buttresses, and analysis of landing loads. Robots could help with that work. A light counter rotating excavator uses paired drums spinning in opposite directions, allowing it to dig without relying on the heavy weight of a large vehicle. It is designed to move on the order of 20 tons per mission, a little more than the weight of 3 large elephants. Covering many 50-meter ships means repeated excavation, hauling, grading, compaction, dust control, repair, and power. The source imagines Optimus robots opening an IKEA-style habitat kit, connecting panels and airlocks, moving ships, and burying them. The individual tasks are real priorities: autonomous clearing, leveling, excavation, boulder movement, compaction, transport, structural assembly, and utility outfitting are all being developed. But certified pressure connections, structural repair, fault recovery, and complete autonomous habitat conversion remain unproven. So not all 5,000 proposed lunar starships need to return. A selected fraction could become stores, workshops, factories, shielding cores, or pressure volumes. The useful comparison is safe usable years per delivered ton. Does conversion beat return and reuse? Does it beat purpose-built modules? We do not know yet. A retained ship can be the first shell. The life inside it still depends on everything that must keep flowing through the steel. The steel can hold an atmosphere. It cannot, by itself, keep that atmosphere alive. Inside any retained hull, life depends on flows. Water moves through pipes. Oxygen enters lungs. Carbon dioxide leaves them. Food, nutrients, heat, waste, filters, replacement parts, and electrical power keep crossing the same boundary. The ship is the container. The settlement is the metabolism. That returns us to the closure scorecard. Water, oxygen, food, waste, construction, power, spares, and resupply do not become closed together. A strong percentage in one column does not fill the others. It only tells us where one particular stream stands. Water is the strongest current benchmark. Modern recovery systems can return about 98% of collected water to circulation, up from roughly 93 to 94% in earlier systems. The achievement is real. Repeated recovery can reduce the mass that must come from Earth dramatically, but 2% still leaves the loop. A permanent settlement needs reserves, delivered makeup water, or a verified local mine and purification system to replace it. And a drinking loop is not the whole water story. Leaks matter. Cleaning matters, agriculture matters, construction matters, filter changes matter. So does contamination that turns usable water into a problem that must be processed again. The number sounds almost complete. It is not the whole habitat. It is one stream. Oxygen is a different stream. A Sabatier system processes exhaled carbon dioxide, the gas people breathe out, to recover some oxygen. In the current path, it recovers about 50% of the oxygen contained in that carbon dioxide. The remaining product is methane, which is discarded. So the water loop can approach 98% while the oxygen loop remains much more open. Not one closed ecology, several different loops, not an atmosphere that maintains itself, a system still needing replacement gases or hydrogen. High recovery is a development aim. Near complete recovery is imaginable in future systems. But an aim is not an operating lunar capability. The distinction is quiet. It is also decisive. Food opens the larger biological gap. Plant chambers in orbit have grown research crops and dietary supplements. They have not supplied complete diets for a settlement. A plant can turn light, water, nutrients, and carbon dioxide into useful matter. But a dependable harvest also needs root oxygen, pollination, disease control, food safety, crop diversity, labor, sensors, airflow, and constant monitoring. Then comes the growing area. A full biological diet may need roughly 20 to 40 square meters of crops for each person. 20 square meters is about a compact one-car garage per resident. Except the ceiling is an intensely controlled light source. The water, nutrients, temperature, microbes, and airflow must all be managed without pause. Those plants need about 250 to 300 watts of photosynthetically active radiation per square meter. Photosynthetically active radiation is the part of light plants use to grow. They may also cycle around 10.8 kilograms of water through each square meter every day, more than 10 large bottles of water moving through 1 square meter of living machinery. But here is the important turn. 10 square meters of agriculture may generate enough oxygen for one person. It may cycle roughly twice the person's water requirement, yet it may produce only about half the food. Not a complete farm. A partial biological machine. Not calories first, air and water first. A green room can begin closing one part of the habitat before it closes another. That is useful. It is not food independence. There is a terrestrial precedent worth holding carefully. A 4-person bioregenerative experiment, meaning an experiment that uses living systems to renew supplies, ran for 370 days. That is a little longer than a year. It reported 100% oxygen and water recycling, met plant-based food needs, and reached 98.2% overall closure. It shows that coupled loops can run for a year with 4 people on Earth. The Moon adds reduced gravity, radiation, dust, restricted inventory, and repair far from a warehouse. A year on Earth is evidence. It is not a lunar certification. The starting flows show why the scale matters. A 4-person mission lasting 30 days uses 288 kilograms of food, 336 kilograms of drinking water, 60 kilograms of water for preparing food, and 108 kilograms of oxygen. It also produces 204 kilograms of trash. At the same planning rates, 20 residents need 48 kilograms of food, 56 kilograms of drinking water, and 18 kilograms of oxygen every day. They produce 34 kilograms of trash. Until local crops replace that food, each group of 20 people adds roughly 1 large suitcase of food to the daily stream. That is before contingency supplies, before a failed harvest, before an illness changes the diet, before a processor loses efficiency. Every new resident is not just another person in a pressure shell. They are another set of flows that must remain balanced. The Moon may help with some of them. Ordinary regolith, the broken rock and dust covering the lunar surface, contains oxygen-bearing minerals. A ground test heated 25 kilograms of simulant, a laboratory material made to resemble lunar soil, to about 1,700 degrees Celsius. That is hot enough to make a kitchen oven seem almost cool. It separated oxygen from the material. This points toward local oxygen and metals. It does not point toward a complete biological inventory. Average regolith figures in one comparison include about 0.011% carbon, 0.0055% hydrogen, and 0.01% nitrogen. Phosphorus and potassium stand at around 0.4% each. Carbon, hydrogen, nitrogen, phosphorus, and potassium are the elements plants require in large amounts. Polar impact plumes have detected water, methane, ammonia, hydrogen, carbon dioxide, and carbon monoxide. A plume is material thrown upward by an impact. It can tell us that volatile compounds exist. It cannot tell us that a city can mine them at a useful rate for generations. So lunar soil is not empty, but it is unevenly useful. Rich in oxygen-bearing minerals, biologically sparse, a place that may provide structure and oxygen before it provides seeds, carbon, nitrogen, vitamins, medicines, or a stable ecology. Waste becomes protected inventory in that setting. Urine, humidity, carbon dioxide, crop residues, packaging, failed polymers, and human waste all contain atoms the settlement cannot casually throw away. Recovery systems must reclaim water and nutrients while stopping pathogens, salts, toxins, and trace contaminants from gathering inside a small loop. And then there is maintenance. A wastewater processor can have sophisticated chemistry and still stop because of a drive belt. One failure was traced to a belt stretching and slipping in condensed steam. An upgraded assembly extended expected runtime from about 1,400 hours, close to 2 months, to more than 4,300 hours, nearly half a year, without replacement. That is maintenance as metabolism. Bearings, belts, filters, seals, diagnostics, skilled hands. A city does not remain alive because its loop once worked. It remains alive because ordinary parts keep that loop working again tomorrow. A credible partial closure milestone would be less glamorous than a declaration of 100% independence. It would run for a full year through crew changes. It would keep water, oxygen, crops, waste, and nutrients stable. It would declare what fraction of calories it produces. It would hold reserves for a greenhouse or processor failure. It would replace common wear parts, and it would report imported mass per resident. That would be a real step. Lower imports, clear limits, demonstrated resilience. Even a settlement that recycles nearly everything still has to pay, for what it cannot yet make. That changes the question. A lunar settlement can begin as a science post. It can welcome visitors. It can carry prestige. But none of those roles alone explains the industrial capital needed to keep expanding a city that still imports its difficult parts from Earth. The source offers a possible answer. An export economy in orbit. AI compute satellites, machines that process artificial intelligence workloads, would use sunlight above Earth and sell computing work back into the larger economy. The moon would eventually supply part of that industrial chain. The filing behind that idea is real. On January 30th, 2026, SpaceX applied for authority to operate up to 1 million non-geostationary data center satellites. Non-geostationary means they would circle Earth instead of remaining above one fixed point. On February 4th, the application was accepted for filing and open for public comment. As of August 2026, the review had begun. Deployment had not been authorized. That distinction matters. A filing is a request to be examined. It is not a fleet. It is not a factory. It is not a revenue stream. The requested ceiling is enormous. The source compares roughly 10,000 active Starlink satellites with a network 100 times larger. Another objection describes 1 million as about 70 times the number of all existing satellites. Picture one moving machine for every person in a large city. Then picture them all sharing the same sky. Spectrum would have to be shared. Spectrum is the limited range of radio frequencies used for communication. Astronomy would have to work around their brightness. Traffic systems would have to predict their paths. And every vehicle would need a safe end-of-life plan. Those problems do not grow in a neat straight line. A larger fleet creates more possible close approaches. More close approaches create more maneuvers. More maneuvers create more chances for a mistake. The requested altitude band includes 900 to 1,000 kilometers, a region some experts already consider close to critical debris density. The proposed geometry is broad. The satellites could operate from 500 to 2,000 kilometers above Earth. That vertical range is like stacking the distance from London to Rome above the planet. Their orbital paths would range from 30 degrees of inclination through sun-synchronous paths. Inclination is the tilt of an orbit relative to Earth's equator. The filing also describes shells up to 50 kilometers thick, a depth like crossing a major city from edge to edge. Optical links would carry most of the network. These are laser links. Narrow beams of light pass between spacecraft. Ka-band radio links would serve as backup telemetry, tracking and command, under conditions meant to avoid interfering with other users. Sun-synchronous does not mean permanent sunlight. It means an orbit crosses the equator at a similar local solar time on each pass. The light arrives from a familiar direction. It does not remain overhead forever. Selected high-altitude shells claim more than 99% sunlight. That is like finding only one dark minute in almost 2 hours. Other satellites would shift their computing load as their available power changed. Now comes the product concept. As of August 2026, the AI-1 design is listed at 30 meters in deployed height and 75 meters in wingspan. 30 meters is a little taller than 9 family cars stacked upright. 75 meters is longer than 7 city buses parked end to end. It lists up to 250 kilowatts of peak compute and 175 kilowatts on average. 175 kilowatts is like keeping 150 old-style 100-watt bulbs lit at once. The same concept lists 75 kilowatts per ton of efficiency. Dividing 175 by 75 implies a mass of about 2.3 tons, about one large pickup truck and another third of one. But that mass is derived from the listed figures. It has not been directly published. At that average specification, 1 million satellites would provide 175 gigawatts of compute. A gigawatt is 1 billion watts. That arithmetic is simple. It is not a commitment to build the fleet. The filing offers a different illustration. It imagines launching 1 million tons each year at 100 kilowatts of compute per ton. That would add 100 gigawatts of capacity annually. 1 million tons is the mass of more than 6 great container ships and another half ship every year. Continuous operation at 100 gigawatts would use 876 terawatt hours in a year. A terawatt hour is a measure of energy over time. It is not a measure of computer performance. It is not a factory output. It is not annual manufacturing capacity. The distinctions sound technical, but they prevent one grand number from becoming 4 different claims. Still, the scale is real. 876 terawatt-hours approaches 7/8 of the more than 1,000 terawatt-hours projected for global data center electricity demand in 2030. One base case rises from 460 terawatt-hours in 2024 to more than 1,000 in 2030, then 1,300 in 2035. That growth gives orbital computing a plausible market to investigate. But plausible demand is not a contract. The application names AI, machine learning, edge computing, and inference. Inference means using a trained AI system to answer or classify something. It provides no signed customers, no prices, no capital budget, no revenue forecast, no break-even model, and then the physical system returns. Space seems cold because there is no air, but vacuum removes convection, the cooling flow carried by moving air. It does not remove heat. Every watt used by a processor becomes waste heat. Every watt. It has to leave through radiators, panels that glow their heat away into space. Not a free refrigerator. A radiator-limited data hall. Not invisible machinery. Large bright surfaces. Solar arrays add area. Radiators add area. Optical terminals need clear sight lines. All of them add mass, visibility, maneuver demands, and collision exposure. The network has its own hard boundary. Some distributed learning tasks may need tens of terabits each second. A terabit is 1 trillion bits of information. An independent concept demonstrated 800 gigabits each way on a bench and modeled 81 satellites inside a cluster with a 1-kilometer radius. Their neighbors could be only 100 to 200 meters apart, about the length of 1 to 2 football fields. This is not a loose ring. It is a tightly choreographed data hall in motion. Fault-tolerant hardware, optical alignment, conjunction maneuvers, radiation correction, all at once. Some inference work may tolerate the delay between Earth and orbit. Tightly coupled computing, where machines must constantly exchange results, may stay on Earth. We do not know which workload mix would pay for the extra launch, replacement, and network burden. Then comes the manufacturing gap. A goal of thousands of AI satellites beginning as soon as late 2027 could be a genuine first step. But thousands are 3 orders of magnitude below 1 million. Not the full fleet. The first factory rung. Not a schedule bridge. A starting point. So the promise has a clear shape. A $1 trillion off-planet compute industry could provide motive, capital, and work for a growing lunar settlement. But no evidence here shows that orbital compute is cheaper. None shows that lunar manufacturing improves its economics. None shows that customers will buy the service, or that its profits would finance Moonbase Alpha. If this becomes a lunar export economy, the next question is what the moon can make before it can make the satellite's most difficult parts. If the satellites are meant to become a lunar export, the first question is not whether the moon can make a chip. It is what the moon can make before the chip. The source makes its largest industrial leap here. It imagines chip fabrication, satellite assembly, and power generation moving away from Earth. The appeal is easy to see. If heavy machinery no longer has to climb out of Earth's gravity well, a growing settlement could eventually build more of its own tools. But a factory is not one thing. It is a sequence. It begins with material, then heat, then power, then the machines that make the next machines. The lunar surface does offer a useful beginning. Regolith is the broken layer of dust, glass, and rock made by billions of years of impacts. It contains oxygen, silicon, magnesium, iron, calcium, aluminum, and smaller amounts of titanium. Those are real industrial ingredients. Still, the material arrives mixed together. Fractured minerals, impact glass, tiny welded grains called agglutinates. The moon is quarry and smelter feedstock. It is not an electronics warehouse. So the first lunar factory would need to excavate the soil, sort it, crush it, heat it, and separate its useful parts. Molten regolith electrolysis is one proposed route. It passes electricity through melted lunar soil to release oxygen and leave metals behind. Carbothermal reduction is another route. It uses heat and carbon chemistry to pull oxygen from a mineral. Prototype work has passed 20 grams of oxygen for each thermal kilowatt hour of energy. 20 grams is about 4 teaspoons of water by mass. The same tests have recovered more than 20% oxygen from regolith by mass. That is encouraging chemistry. It is not a mine. One Highland simulant run processed 25 kilograms over 36 hours. 25 kilograms is about the mass of a large checked suitcase. 36 hours is a day and a half. 24 of those hours were electrolysis under lunar-like vacuum and thermal conditions. The temperatures tell us what the machinery faces. Some routes run above 1,600 degrees Celsius. One molten test reached around 1,700 degrees Celsius. That is furnace heat, far beyond anything in a kitchen. It can prove that atoms separate as expected. It does not prove that a robotic mine can feed a furnace every day, repair it after a fault, and keep its product pure. As of August 2026, terrestrial simulant work has made or targeted iron, silicon, aluminum, oxygen, slag, solar cells, cover glass, and aluminum wire. Slag is the stony material left after useful metals are separated. One reported silicon purification exceeded 99.999%. That leaves fewer than 1 part in 100,000 impure. Cover glass-supported solar cells are projected to last more than 10 years. A decade is a long service interval for a surface panel, but these are Earth-based trials with Moon-like material. The Moon has not yet operated this industrial chain for itself. That difference sets the first manufacturing phase. Make oxygen. Make bulk alloy feedstock. Make slag, glass, ceramics, sintered parts, shielding, berms, pads, foundations, and simple structural members. Sintered parts are shaped grains fused by heat rather than fully melted. These products are not glamorous. They are exactly where local production can matter first. They are heavy. They are repetitive. They can replace the largest imports. The second phase adds more delicate bulk work. Aluminum wire, thick film antennas, conductive layers printed onto a surface, glass covers, solar substrates, the supporting layers beneath a solar cell, repeating trusses, thermal panels, tanks, repair blanks waiting to be machined into a needed part. Farview gives this middle ground a useful shape. It is a proposed far-side radio array with 100,000 dipoles, simple paired antennas, listening between 5 and 40 MHz. 100,000 is enough repeating hardware to fill a large stadium with one antenna at every seat. A megahertz is 1 million cycles each second, like tuning across a particular slice of the radio dial. The concept could use local antennas, solar cells, and power lines, while receivers and later upgrades arrive from Earth. Its area is not settled. One description gives about 200 square kilometers. Another gives roughly 20 kilometers by 20 kilometers, or 400 square kilometers. The larger figure is a square 20 kilometers on each side. We do not need to average the conflict to see the lesson. Both versions spread repeating hardware across a vast site. That is where lunar material has an advantage. A radio array needs immense lengths of wire. It needs glass, supports, power surfaces, and repeated antenna shapes. It does not need the Moon to make every receiver first. And that is the third phase. Hybrid satellite assembly. The Moon makes the large body. Earth still provides the compact intelligence. Processors, memory, radio frequency receivers, sensors, precision bearings, radiation-hardened electronics, and difficult chemicals would remain imported longest. A satellite looks like an electronic object from a distance. Much of its area is not electronic. Structure, solar array, radiator, antenna, wire, shielding, tankage, not an imported whole, not an independent lunar chip industry, a hybrid machine. The distinction becomes sharp inside a modern chip fab. A fab is a factory that makes semiconductor chips. the tiny patterned pieces of silicon that process information. It contains more than 1,000 tools. One illustration counts about 1,200 production tools and another 1,500 utility units. That is roughly 2,700 specialized systems working together. More machines than many small factories contain in total. The illustrative cost is about $10 billion. That is the scale of a major city infrastructure program. Construction takes 3 to 5 years on Earth, where suppliers, trained workers, replacement parts, clean water, stable grids, and chemical plants already exist nearby. The fab is a chemical city. It needs ultra-pure water, water cleaned far beyond ordinary drinking quality. It needs controlled air, electricity, cooling, vacuum, metrology, deposition, photolithography, etching, cleaning, polishing, solvents, acids, slurries, targets, dopants, and specialty gases. Metrology means measuring parts precisely enough to know that a microscopic pattern is correct. Photolithography uses light to print those patterns. Dopants are carefully added atoms that give silicon its electronic behavior. One terrestrial example uses nearly 4 million gallons of water each day. That is enough water to fill several Olympic swimming pools. Only 20% returns directly before more treatment, 1 gallon in 5. A lunar process would not have to copy that design. But silicon plus vacuum is not a fab. It is the beginning of a much longer inventory. Natural vacuum can still help. It may simplify some deposition work, where thin material layers are placed on a surface. It may help electron beam processors, which use focused electrons to heat or shape material. It can reduce oxidation, the unwanted chemical attack that occurs when hot materials meet oxygen. But vacuum does not equal cleanliness. The moon is a factory room already pumped down. Outside the door is a hostile loading dock. 1/6 gravity changes how powders settle, how fluids separate, and how printed layers behave. A 6-kilogram box would weigh about like 1 kilogram in your hand. Sharp charged dust can enter seals and surfaces. Thermal cycling can shift a precision alignment again and again. A fabrication room would still need sealed clean zones, stable temperatures, filtration, radiators, dust-free transfer, spare tools, and inspection equipment. The rational import rule is quiet and powerful. Make the mass heavy, repetitive, chemically simpler body locally. Import the light, complex, high-value pieces for as long as necessary. That rule does not diminish the moon. It gives it a reachable job. First the oxygen, then the metal, glass, wire, and solar surface, then larger assemblies, then the equipment that makes more of each. Local production becomes self-growing only when mining, power, furnaces, wire, glass, assembly, measurement, and repair equipment can expand their own output. A settlement that imports replacement furnaces and imported metrology can still make useful things. It is not yet reproducing its industrial base. And once that body can be made, the next question is how it leaves the moon at all. Making the body locally removes one launch from Earth. It immediately creates another. How does that new lunar made mass leave the moon at all? The elegant answer is the mass driver. A mass driver is a linear electric motor, like an electric train motor opened into a straight line. It accelerates a magnetically supported bucket along a track. The bucket releases its payload. Then it slows down and returns for another load. No chemical propellant is burned during that first push away from the lunar surface. That is a real advantage. Lunar material does not need to carry its own fuel from the ground. But the first push is not the whole journey, not the final journey. The first push. Laboratory hardware has shown why the idea persists. One sequence exceeded 30G, another approached 500G, a third passed 1600G, with 1800G sighted at full power. AG is the force we feel from Earth gravity. At 30G, a 10-kilogram bag of flour would press like 300 kilograms. At 1800G, it would press like 18 tons. The experiments showed acceleration. None showed a working lunar export system. The trade is direct and unforgiving. A payload needs about 2.44 kilometers each second to leave the moon in one table. That is more than 2 highway kilometers every second. Give it 33 G, and the track stretches to 8,905 meters, roughly the length of 90 city blocks. Raise the acceleration to 500 G, and the track can shrink to 587 meters. Raise it to 1800 G, and it can shrink to 160 meters, a little longer than one city block. But a shorter rail asks more of the payload. Batteries have layers. Optics need stable alignment. Deployable panels have hinges. Electronics have tiny connections. All can be redesigned. None are automatically hardened for hundreds of G. The track is not merely a length of metal. It is a decision about what kind of cargo the moon can afford to throw. One historical concept embraced the rugged option. It would launch 5 sintered regolith blocks each second. Sintered regolith is lunar dust fused by heat into solid pieces. Each block weighed 10 kilograms, about a full bag of soil. Together, 50 kilograms would leave every second. The speed was 2,400 meters per second, faster than 2 kilometers each second. The proposed motor track ran for 10 kilometers, a trip that would take more than 2 hours on foot. A drift section followed. Then came a 3-kilometer bucket decelerator, a braking rail almost as long as a long walk across town. At 70% duty, meaning the system operated for 7/10 of its available time, the design projected 1.1 million tons each year. That is the mass of roughly 60,000 ordinary cars. Now comes the hidden factory. The launcher alone was assigned 192 megawatts. That's enough to keep nearly 2 million old-style 100-watt bulbs lit. The full base needed 200 megawatts. The launcher weighed about 4,000 tons, like a line of 200 loaded city buses. The power plant added 9,900 tons, close to 500 loaded city buses. 2 complete launchers and nuclear power were proposed, so the system could continue through the long lunar night. And the blocks were not aimed directly at an ordinary Earth orbit. They traveled toward Earth-Moon L2, a balancing region beyond the moon where gravity can help hold a receiver in place. There, an active catcher would have to meet them. The catcher weighed 220 tons, around the mass of 36 loaded city buses. Its working area was 0.43 million square meters, roughly the floor area of 60 large supermarkets. It had to collect blocks arriving at 200 meters per second. This was the catcher's mitt. A net only 10 square meters across, about the floor of a small bedroom, moved through a triangle with sides 1 kilometer long. It had to keep station, meaning it had to use propulsion to hold its planned place. It would also make nearby navigation dangerous during operation. The launched material still needed a destination that could reach out and take it. It still needed a second machine. That is where vacuum exchangers one difficulty for another. No air means no drag and no weather. It also means the rail must aim almost perfectly. The path direction error was below 0.01 meters per second. The crosswise error was below 0.01 meters per second. In some ranges, track alignment had to remain below 0.01 centimeter, thinner than a human hair. A railway whose final aim is set thousands of kilometers away. Surveying becomes propulsion. Foundations become guidance. Dust control becomes navigation. The lunar surface makes each of those jobs harder. Its dust is sharp, electrically charged, and insulating like tiny glass shards around a precision railway. The track also faces about 112 degrees Celsius in daylight, hotter than boiling water, then minus 173 degrees Celsius at night, far colder than a household freezer. This cycle lasts 29.5 days, nearly a month. Rails expand, foundations shift, coils gather dust. The alignment has to be measured again. A later study chose a gentler, slower approach. It modeled chunks of 30,000 kilograms, the mass of about 5 loaded city buses. The launcher would accelerate them at 20 G to 1,700 meters per second, along a 7,400 meter track, a distance near 7.5 kilometers. Its projected output was 2 million kilograms a year, about 114 common lunar modules. The launcher mass was 36,800 kilograms, around 6 loaded city buses. With power and storage, it became 57,600 kilograms, roughly 9 loaded city buses. The model used 295 kilowatts, like keeping 2,150 old-style bulbs lit, assuming 92% of electrical energy became motion. But this was a different task. The fast system was a commodity stream aimed at an L2 catcher. The slower system sent large chunks toward lunar orbit and assumed reaction control. Small rocket thrusters used to correct residual error. Neither one placed an ordinary satellite into useful Earth orbit by itself. Orbit is not just speed. A payload can fall into Earth atmosphere. It can miss capture. It can escape along the wrong path. One separate architecture needed 12 aerobraking passes, using repeated brushes through an atmosphere to slow down, totaling 3,100 meters per second of velocity change. A crew version used rocket propulsion instead. Guidance, capture, aerobraking, propulsion, or a receiver must still finish the trip. Wait. A spacecraft surviving a rocket launch does not settle the problem. Conventional small satellite testing uses around 10 GRMs vibration for 2 minutes. GRMS is a way of measuring the average strength of a changing vibration. Sustained 20 or 30 G is another load. 500 G is another world. 1800 G is another world again. Rugged material may survive. A delicate satellite would need a fundamentally different design. There is also the path nobody wants to use. A release error makes hypervelocity debris, material moving so fast that a small piece can do severe damage. Launch corridors, catcher misses, orbital traffic, coil faults, bucket faults, safe shutdown, emergency disposal, and protected regions all become part of the machine. A rail on the moon still needs rules around the moon. One economic model favored the driver over all lander transport only when lunar propellant cost more than $250 per kilogram, about the price of a full grocery bag by mass. That is not a universal threshold. It is a reminder that the case depends on throughput and on the cost of the alternative. The mass driver removes the first chemical engine. It does not remove the power plant. It does not remove the track. It does not remove payload hardening, precision, capture, maintenance, or safety. No complete lunar driver, receiver, and useful orbit delivery system has yet been demonstrated. The next test is not whether the rail can throw material. It is whether a lunar settlement can build the quiet network around it that lets the material arrive somewhere useful. That network cannot float in an illustration. It has to cross real ground, draw real power, and connect to a real mine. The render gives us a useful clue. It shows solar fields, factories, habitats, batteries, a mass driver waiting at the edge of a crater. It captures why the lunar South Pole has become such an important region. But it is not a blueprint. A picture can place every machine beside every other machine. The moon cannot. The pole has a rare advantage. The moon tilts by only about 1.5 degrees, like a plate raised just slightly on one side. Sunlight skims across the polar ground, rather than climbing high overhead. Shackleton Crater is about 19 kilometers across, a distance that would take a long walk across a city. 3 points along its rim receive sunlight collectively for more than 90% of the year. Below them sits an interior that remains permanently shadowed. At first, this sounds like the perfect address. Light above, ice below, industry in between. But here's where it gets strange. No point there stays illuminated forever. The useful light falls on separated high places. The cold traps that may hold water sit in darkness below. Not a single lot. Several connected properties. The South Pole is a split-level industrial site, with power on ridges and possible volatile deposits in craters. That changes the city completely. It needs roads or carefully planned routes. It needs cables or beamed power carried without a wire. It needs relay stations, storage, mines, and shelters. It needs machinery that can travel safely between unlike environments. The distance may look small from orbit. The operating boundary is not. Even the familiar Artemis shorthand needs care. Shackleton Crater was not simply selected as the landing site. NASA considered 13 candidate regions, including Peak near Shackleton, Connecting Ridge, and Connecting Ridge Extension. The final choice depended on the launch date, terrain, lighting, communications, and other conditions. One early plan sought 6.5 days of lighting access. That is not permanent daylight. It is a carefully chosen window. Water has the same layered story. Several permanently shadowed places show surface ice signatures. An impact into a polar crater lofted grains of water ice. And sunlit soil in Clavius contains molecular water, about one 12-ounce bottle spread through a cubic meter of soil, roughly the space of a large washing machine. The water is real. The reserve is not yet defined. The presence is confirmed. The mine is not. The source speaks of hundreds of millions of tons of crater ice. It also places 50 to 70% of accessible near-surface lunar ice near the South Pole. Those are claims about abundance, not qualified mine inventories. From orbit, we still do not know the grade at a chosen site. We do not know the thickness. We do not know whether the ice is a layer, scattered grains, cemented soil, or something harder to reach. And we do not know the sustained recovery rate. As of August 2026, the prospecting work remained early. A polar drill was designed to reach about 1 meter down, taking samples in segments about 10 centimeters long, close to the length of a hand. It would heat those samples and analyze the released gases. The lander reached within about 250 meters of its target, about 2.5 football fields, but ended on its side. Some objectives were completed. Analysis continued. This was prospecting, not mining. The mining chain is longer than the render suggests. First, equipment excavates icy regolith, the broken rock and dust covering the moon. Then it heats the material. Water vapor has to move into a cold trap, a cooled chamber that condenses vapor back into liquid or ice. The water must be purified. Electrolysis then splits it into oxygen and hydrogen using electricity. Both products need storage. Every link must keep working. In darkness, in dust, with no repair shop nearby. A thermal mining experiment with a goal of 1 kilogram of ice shows one piece of this work. Terrestrial oxygen processing tests show another. They are not a continuous lunar plant. They are not a mine operating through years of shifts. The path from sample to supply is still open. Power is where the difference becomes hardest to ignore. Heating, life support, mines, furnaces, manufacturing, satellite assembly, cryogenic production, storage, and the mass driver all draw from the same future grid. A true industrial city reaches toward gigawatts. A gigawatt is 1 billion watts, the scale of a major terrestrial power station. The current fission design point is 40 kilowatts for lunar use in the early 2030s. That is described as enough power for about 30 households for 10 years. 1 gigawatt equals 25,000 of those units. Not a small step. A scale gulf. The comparison does not prove a gigawatt grid cannot be built. It shows what has not yet been crossed. Solar power does not erase that gulf. High ridges reduce periods of darkness. They do not eliminate them. A literal ring of panels around a crater would not work like the clean line in a render. Arrays need graded ground, dust removal, transmission lines, switching equipment, access for maintenance, and redundancy across separated peaks. The city needs power where the machines are, not merely sunlight somewhere nearby. Away from favorable polar light, lunar night lasts about 14 Earth days, nearly half a month. Batteries can bridge shorter darkness and sudden changes in load. Industrial reliability needs more. It needs long-duration storage, continuous generation, transmission, load shedding, meaning lower priority equipment is turned off to protect essential systems, and black start capability, the ability to rebuild the grid after it has gone dark. Then comes the thermal boundary. With no atmosphere, equipment gains and loses heat mainly by radiation and through what it touches. At equatorial examples, the surface can reach about 302 degrees Fahrenheit in daylight, hotter than boiling water. At night, it can fall to minus 292 degrees Fahrenheit, far colder than any household freezer. Permanently shadowed regions can reach minus 418 degrees Fahrenheit. A miner driving from a lit ridge into a crater crosses more than distance. It crosses into a different thermal world. Dust follows it everywhere. Lunar grains are sharp, abrasive, adhesive, electrically mobile, and insulating. They behave like tiny glass shards that cling like hair to a rubbed balloon. Apollo crews found them in boots and seals. The dust clogged mechanisms. It irritated noses. It wore down surfaces, stabilized roots, filters, sacrificial interfaces, tolerant fabrics, and electrodynamic shields that use electric fields to move dust away are not housekeeping. They are part of the settlement. So is protection from radiation. An instrument measured an equivalent dose of about 60 microsieverts each hour on the lunar surface. A microsievert is a very small unit used to measure radiation dose. Regolith shielding and storm refugees can reduce danger during solar particle events. They do not erase galactic cosmic rays, high-energy particles arriving from beyond our solar system. The long, quiet exposure remains. And then, there is gravity. The moon offers 1/6 of Earth gravity, like carrying only 1/6 of your usual weight. That may be enough to help the human body. It may not. We do not know whether it prevents continued bone and muscle loss over years. Exercise may help. Intermittent artificial gravity may help. No person has lived for years under lunar gravity. The settlement would be learning that answer while people live inside it. The proof of success is not whether someone on Earth can see a bright city on the moon. It is stable power, mined and purified water, machinery repaired after it fails, closed life support loops, protected crews, a capacity that grows. Once the city is understood as that network, its future has to be earned one capability at a time. Once the city is understood as that network, its roadmap cannot be one date on a calendar. It has to be a sequence of things that work. The source gives us a bold calendar. Possible uncrewed Starship landings in 2027, cargo building through 2030, crews in the early 2030s, population growth by the middle of that decade, partial self-sufficiency by late 2030. There is a problem inside that sequence. Late 2030 arrives before much of the early 2030s, and mid-decade work has been completed. The dates may express the direction of travel. They do not yet form an approved schedule. The same care applies to readiness. The source describes Starship V3 as weeks away, and suggests that lunar iteration could move at least 10 times faster, sometimes 10 to 20 times faster. As of June 2026, V3 payload delivery was still expected in the second half of 2026. More frequent access to the moon could certainly create more test cycles, but a faster flight rhythm does not make every dependency mature at the same speed. A connector still has to mate. A pump still has to run. A crew still has to survive its worst day. On the current path, 2027 is not the planned landing. It is a low Earth orbit integration demonstration. The lander must rendezvous and dock. Life support, communications, propulsion, and suit interfaces must work together. The first landing is targeted for 2028 as of August 2026. The intention after that is at least one surface landing each year. That is not a disappointment. It is the right kind of beginning, not a city. An integration test, not a permanent population. A chain being checked, link by link. Phase 0 happens before the moon is even in reach. Starship has to fly repeatedly as an integrated system. Vehicles have to be recovered, inspected, and prepared again. Cryogenic propellant, fuel kept at extremely low temperatures, has to move between vehicles in orbit. A depot, an orbital fuel store, has to hold that propellant. Ships must rendezvous, dock, and transfer it autonomously. Tanker operations must become frequent enough to fill the system. Crew life support and suit interfaces have to be ready. And the final cargo configuration needs a measured lunar payload, not an orbital target standing in for one. This is the part that a reusable lander cannot skip. The proposed crewed chain includes a depot campaign, more than 10 tanker flights, and more than 200 days of aggregation before the lunar mission can proceed. We have already seen why that chain is demanding. One successful vehicle is not the same as a functioning fuel network. The moon waits at the far end of every link. Phase 1 is uncrewed lunar proving. Fill the depot, fly the lander, reach lunar orbit, check the spacecraft there, land precisely, deploy power and communications, unload cargo, connect equipment, run dust-tolerant mechanisms, survive the thermal environment, then shut down safely. The order matters because machines should find the incompatibilities first. A cargo pallet may land perfectly and still refuse to release. A power cable may reach the right connector and still fail to mate. A rover may work in sunlight and stop in shadow. These are not small details. They are the experiment. Phase 2 brings people into that experiment for short sorties. One reference habitat describes 2 crew members for stays of up to 30 days. Later missions could support 4 people for up to 60 days. Early on, consumables may still dominate the manifest. That is acceptable if the purpose is clear. Test medical response. Test radiation shelter. Test mobility, maintenance, construction, and emergency return. Learn which ordinary failures can wait and which cannot. Then comes Phase 3, the foundational outpost. Habitat modules in the 100 cubic meter class begin to create real internal volume, roughly the enclosed space of a modest home. Airlocks follow. So do aggregation nodes, places where cargo and services are brought together. Relay coverage, navigation, solar distribution, storage, regenerative water and atmosphere systems, meaning loops that recover material for reuse. Early resource prospecting begins alongside longer stays. But here is the important correction. This is still an outpost supply chain. Current foundational demand is discussed in ranges of about 2,500 to 10,000 kilograms each year. That is the mass of several family cars to roughly the mass of a large city bus. Some occasional elements could reach 15,000 kilograms. One planning analysis identifies a capability gap between 500 and 12,000 kilograms. Another goal reaches up to 8 tons per 28-day mission. These are serious logistics problems. They are also measured in thousands of kilograms, not in million-ton industry. The scale gap is the reveal. Not a city manifest. An outpost manifest. Not industrial closure. The first durable delivery routes. A growing outpost also needs to hear, see, and coordinate its own work. Current planning begins with a 5-satellite relay constellation. After that, a second provider matters. Surface networking, navigation and timing, safety video, direct links to Earth, and interoperable services must follow. Interoperable means systems made by different groups can connect and operate together. This is where dissimilar logistics becomes a safety feature. If one vehicle type is grounded after an anomaly, the settlement cannot be left waiting for a single investigation to end. Different cargo providers and different cargo sizes create alternate routes through the supply chain. A network can bend around one missing route. A single line cannot. Phase 4 is sustained lunar evolution. Occupancy becomes continuous or nearly continuous. Medical and emergency capability grows with the population. Power distribution reaches farther. Autonomous cable deployment becomes necessary. Dust-tolerant connectors have to work repeatedly. Rovers need charging. Local oxygen and construction pilots must operate outside a laboratory. And equipment has to travel reliably between illuminated ridges and possible mines in shadow. The planned 40 kilowatt class fission system belongs in this phase, with an early 2030s target as of August 2026. It is an important step. It is not the future industrial grid. The difference remains large. That is why the roadmap must record installed power, transmission, storage, and repair performance, rather than treating one delivered reactor as a final answer. Phase 5 is partial independence. The settlement should sustain its 98% water recovery while adding local makeup water. It should improve oxygen closure. It should state exactly what fraction of food calories it produces. It should recover nutrients. It should make shielding, roads, landing pads, glass, wire, simple metals, solar components, and common repair parts. It should also hold reserves for missed cargo. One measure gathers all of that work into a single honest question. How much mass must still arrive from Earth for each resident each year? If that number falls while safety improves, the settlement is becoming less dependent. If it rises, the city may be getting larger without becoming stronger. Phase 6 is harder still. This is self-growth. Habitat, power, mining, processing, farming, and manufacturing must expand faster than imported productive mass rises. Productive mass means the machines and tools that make more useful capacity possible. A locally made piece of equipment must help enlarge the local factory that made it. A larger population must add operators, knowledge, and redundancy faster than it adds maintenance and demand. That is the first real spark. Not the first landing, not the first flag. The first moment when local capacity begins to reproduce itself. Hardware alone cannot cross that threshold. Governance arrives before independence. On July 17, 2026, 70 signatories had joined the Artemis Accords, sharing principles for peaceful use, transparency, interoperability, emergency aid, registration, data sharing, resources, and harmful interference coordination. A lunar city needs more than principles. It needs labor rules, medical authority, liability and rescue obligations, agreements about property and resources, a way to resolve disputes, and local authority when an operational emergency cannot wait for terrestrial direction. Medical capability must scale in the same way. How many people can be sick at once? What care cannot wait for a return flight? How quarantine works? Where pharmacy supplies come from? Who manages dental and surgical emergencies, mental health, radiation monitoring, and evacuation? These questions become more serious as a base becomes a town. Financing has its own phase transition. Government exploration, delivery contracts, private investment, resource services, communications, science, tourism, and hypothetical orbital computing may each pay for part of the work. None is guaranteed to arrive as a trillion-dollar market on the needed date. A settlement cannot base its life support on a revenue stream that has not yet appeared. And then comes the final threshold. A base that imports food, chips, medicine, launch services, and critical spares from Earth shares Earth failure. It may be occupied. It may be useful. It may be historic. It is not yet a separate refuge. Genuine resilience requires a long interruption in supply. It requires a viable population, preserved knowledge, power, food, repair of critical systems, and decisions made without terrestrial command. No validated threshold tells us when that state begins. No approved calendar can supply the answer. The dates can still motivate us. But the next rung has to be earned before the ladder can carry anyone farther. The dates can move, but the truth of each rung cannot. That is what changes the apparent turn away from Mars. Moonbase Alpha first looks like a new destination, a choice to leave the red planet behind for the nearer grey world. After following the whole chain, it looks different. The moon is the place where the first decisive settlement experiment can happen closer to Earth. Mars remains ahead. The moon is the nearer laboratory. The source imagines an under 10-year path to a lunar city and a 20-plus year path to Mars. Those dates may change. The order still makes sense. First an uncrewed landing, then cargo, then cruise, then a permanent population, then partial closure, then self-growth. Machinery should fail before people rely on it. Ecological loops, systems that keep air, water, and food moving in circles, should settle before a population depends on them. A landing proves arrival. It does not prove survival. A permanent population proves endurance. It does not yet prove independence. The first proof is modest. Humans remain on the moon for long periods. They recover most of their water, perhaps near the 98% benchmark. They generate oxygen. They survive radiation events. They repair common failures. They keep power running through local darkness. That would matter enormously. More than a visit. Still an outpost, more than a flag, still dependent. But here is the next turn. The second proof is not simply that people can live there. It is that the moon begins to supply the work of keeping them there. Regolith, the crushed rock and dust of the lunar surface, becomes shielding. It becomes roads and landing pads. It becomes oxygen, glass, wire, simple metal parts, solar surfaces, and the raw material for later factories. Then a number begins to change. Imported mass per resident begins to fall. The moon is no longer only the endpoint of a supply chain. It has entered its own supply chain. This is where a settlement changes character. Not a warehouse at the far end of Earth's transport network. A place starting to make some of its own necessities. Not complete independence. A growing share of the work done locally. The decisive proof comes later. A settlement adds habitat, power, food production, mining, repair, and manufacturing without importing an equal amount of productive capital. Productive capital means the machinery, tools, and systems that allow more useful capacity to be made. It misses a resupply. It continues operating. It keeps expanding. That is self-growth in operational terms. Capacity rises. Imports per resident fall. The system learns to make more of the system. At that point, the moon becomes a design library for Mars. Every modular interface leaves a record. Every failed seal leaves a lesson. Autonomous maintenance, machines detecting and correcting ordinary problems without waiting for a person, becomes a tested routine. Life support produces real measurements. Dust-tolerant connections, resource plan controls, crew procedures, governance rules, and multi-provider integration all become things that have been tried under pressure. That knowledge travels outward. It does not travel perfectly. Mars still requires months of transit. A message can take 4 to 24 minutes one way. Launch opportunities arrive about every 26 months. Mars has an atmosphere, which means entry and descent through air must work before a crew leaves Earth. It has different gravity, different dust, different chemistry. Its infrastructure has to be ready before people arrive. The moon cannot rehearse all of that. It cannot make Mars easy. What it can do is reduce a different kind of uncertainty. The uncertainty inside the settlement itself. How do people keep a remote habitat alive? Which parts fail first? Which repairs can be automated? Which supplies must be held in reserve? Which interfaces let different builders work together? That is a serious advantage. A lunar failure can return as data sooner. A Mars failure may wait months for an answer. The distance matters, but the feedback time may matter more. This also changes the place of the grander visions. The AI economy, a full chip factory, 1 million satellites, 5,000 starships, an 8.2 launch per day cadence, a gigawatt grid, and a mass driver may become later layers. They may be useful. They may even become necessary for a much larger lunar economy. But they do not have to arrive before the first meaningful proof. Requiring every layer in 1 decade makes the strategy brittle. Measuring each layer by what it actually adds makes it adaptive. 1 good repair system, 1 dependable power network, 1 useful local material stream, then another. Profit belongs in that picture, but it cannot define success. Communications, science, manufacturing, energy, tourism, or orbital computing could attract capital. We do not know whether any one of them becomes a durable engine. A market can contract, a business model can fail. The air still has to circulate. The water still has to return. Medical care, food, maintenance, and local authorities still have to endure. And then the meaning of multi-planetary resilience becomes clearer. 1 cargo-dependent outpost does not protect civilization. A settlement that preserves knowledge, maintains a healthy population, produces food and power, replaces critical machinery, and makes its own decisions begins to do something more profound. It begins to share fewer of Earth's single points of failure. The moon does not need to become Earth. It does not need forests, open oceans, or a natural biosphere. It needs human systems that remain alive long enough to learn, repair, and reproduce themselves. A small, maintainable version of habitability, carried outward. That is the strongest version of the Moon first idea. Not choosing the Moon instead of Mars, not announcing a city on a deadline, shortening the feedback loop of failure. Each return can turn a claim into data. Each repair can become a better design. Each generation of hardware can leave the settlement less dependent than before. And if that pattern holds, the Moon becomes more than a nearby destination. It becomes the first place where civilization learns how to carry its own continuity beyond Earth. Then Mars becomes less abstract. So do the asteroids, the outer planets, the larger solar system, and perhaps places beyond it. Not because the journey has been completed, but because a second center of life and work has learned how to grow.